Hi, this is Dr. J, and I'm going to talk about the linearity property of the Laplace transform. And I'm going to provide an example of how to use the linear property of the Laplace transform. And on the next video, I'll use this property to find the Laplace transform of a sine function. Here in the next couple slides, I'm going to explain what we mean by linearity. Here we take a scaled input. Here we have an input x1 scaled by a constant a, and we're going to transform it or do some mathematical operation. In this case, I'm doing a Laplace transform, and we have a corresponding scaled output as a result of this transformation, given as a, the constant, times x1 of s, the Laplace transform of x1 of t. We're going to take another input scaled by b, x2, and then perform a transformation, and we get its corresponding Laplace transform b x2 of s, and we're going to add them all up, and then we can also take a third, and you can see we can extend this to many inputs when we try to find the Laplace transform of a generic function. And here it's scaled by c, x of 3, and we got the corresponding output c x3 of s. We take all those and we add it, and we get a new Laplace transform as a result of summing all these outputs resulting from the Laplace transformation. So that's our output coming out of this summer. So this is a block diagram of to express the linearity function. And we saw that the output is the sum of the individual outputs due to each of these inputs here. And we have the corresponding outputs, and the outputs is just the sum of it. Is to break up the inputs into individual inputs, add them all up, and get an overall input, and then perform the operation on the total sum of each scaled input. So we perform a transformation, and we get an output x of s, which turns out to be the same one on the previous slide. A x1 of s plus b x2 of s plus c x3 of s, where a, b, and c are all constants. So when the output of each of the previous two slides, namely this one and this one, when they have the same output, then we say the system is linear. Again, note the difference between these two diagrams. Here, we're taking each input and we're operating on each input. Then we take the resulting output due to each input and add them all up. In this other diagram on the right here, we're just breaking up the inputs, adding up all the inputs, and then performing one operation on this total sum due to each input. And if the output from this diagram and from this diagram are the same, then we say that the transformation, the Laplace transformation, is linear. So let's look at a mathematical proof very quickly, short and sweet. So here we're given the Laplace transform for a linear combination of inputs. In this case, it's f1 and f2, weighted by or scaled by constants a and b. We want to show that it's equal to a f1 of s plus b f2 of s. And here we're going to use the definition of the Laplace transform to show that this is true. To save on the writing, we have this subscript L to define this mathematical operation called the Laplace transform. And so the Laplace transform of this linear combination of inputs, applying the mathematical definition of the Laplace transform, we have here, and pulling out the constants a from the integral, we have basically our definition of the Laplace transform here for f1 and here, after pulling constants out a and b. And that's our proof. And just a quick note, going from the Laplace domain to the time domain, the inverse transformation is also linear. So let's apply this example of linearity. and show that the Laplace transform of this function, f of t equal the constant a times the quantity 1 minus e to the minus alpha t multiplied by a step function u of t. You can think of this as a model of a charging capacitor. And we want to show that the Laplace transform for this function is equal to this, f of s, which is equal to a alpha divided by s multiplied by the quantity s plus alpha. So we're going to use our definition of the Laplace transform defined by the subscript L. So we're operating on f of t with this mathematical operation L, Laplace transformation. And the Laplace transformation of f of t is equal to Laplace transformation, and it's just a direct substitution of our definition of f of t. And we're going to break up this Laplace transformation into two pieces since it's linear. So now we have for f of s, it's equal to a times the Laplace transformation of the step function, which we know, minus a times the Laplace transformation of exponential that we know from earlier videos. So the Laplace transform of a step is a over s, 1 over s multiplied by a, and the Laplace transform of an exponential is 1 over s plus alpha scaled by a, and there's a minus sign in front of it. And when you put it in the common denominator of s multiplied by s plus alpha, and we put it at the common denominator where we have s multiplied by s plus alpha, we have a times the quantity s plus alpha minus as. And we see things will cancel. Here the as cancels. And we're left with alpha in the numerator multiplied by a divided by s multiplied by the quantity s plus alpha. Therefore, the Laplace transformation of f of t is equal to a alpha divided by s times the quantity s plus alpha. And that's what we want to prove. And we use the property of linearity to accomplish this. We also use the Laplace transform of a step and the Laplace transform of an exponential. On the next video, we'll show you the Laplace transform of a sine function using the property of linearity. Signing off, Dr. J.